So good morning, everyone. Just sorry for my voice if someone cannot hear from the back. Just raise your hand. Okay, thank you. So my name is Pietro Mini. I'm a PhD candidate at Politecnico di Milano under the supervision of Professor Lorenzo Mario Fagiano. And today I will present you my master thesis work, which is entitled Hydrogen Production from Offshore Airborne Wind Energy, System Modeling and Cost Analysis. So this research mainly focuses on two topics, which are airborne wind energy and hydrogen production from renewable resources, which are both quite important in the context of the energetic transition and the decarbonisation. As probably everybody here knows, one of the most important goals is to keep temperature increment 1.5 degrees below the pre-industrial level. So we have to employ some new technologies, which are these ones. And we can clearly see that renewables will be one of the leading forces to the change. But there is also hydrogen and the development of an hydrogen market, which is quite important. And as we can see here, today only the 4% of the hydrogen which is produced come from electrolysis process, which is the only one that can be seen as sustainable if it's from renewable energy. So in this term, we want to investigate the possibility to create a facility for hydrogen production starting from offshore airborne wind energy. And this is the scheme of the facility with the different components that we inserted. And we can identify three main areas. So the first one, which is the one of energy production with airborne wind energy system farm and a battery energy storage system. Then we have the hydrogen production area with the electrolyzer and the water treatment system. And finally, the preparation for transport, which includes the compressor and the storage. So regarding energy production, the idea is to create an airborne wind energy system farm in offshore environment in order to exploit marine winds, but also to avoid problems of land occupation. And the idea is also to guarantee a sort of production continuity in time, as we can see here. So the idea is to alternate the phases of traction and retraction of the different airborne wind energy system, so to compensate for the moments in which we have to retract the kite, and so we have to use part of the energy. And the other idea is to introduce a battery energy storage system, just to be like an emergency buffer in case of faults or problems, so in order to supply energy to the facility. So the other area is the hydrogen production area. So the main element is the electrolyzer, which is the component that permits to transform energy and water into hydrogen, thanks to electrolysis process, which happens in the electrolyzer stuff, which is this part. And we have to say that the hydrogen requires high purity level water, and we wanted to use directly seawater. So we have the need to use another element, which is the water treatment process. And this is a reverse osmosis process, so we want to eliminate the salty part from marine water in order to directly supply water to the electrolyzer. And finally, we have the preparation for hydrogen transport. So hydrogen has a low volumetric density, so this means that occupies large spaces if it is not compressed. And so the idea is to use a reciprocating compressor, so to increase the pressure of hydrogen in different stages from a value of 80 bar, which is the value at the output of the electrolyzer, to a value of 200 and 220 bar, which is a safety value for transporting two vessels. So once we reach the desired pressure, we can insert hydrogen into these tanks, which in this case were chosen as type 1 tanks, which means made by a thinner layer of metal. And then we also identified 4 locations in order to test the performances of the facility. These locations are Hornsea in UK, Viana do Castelo in Portugal, and Marsala and Olmi in Italy. The main concept behind these 4 is that we want to have a good wind speed average at 500 meters above ground. But we have also some other constraints, and in particular for the first 2 locations, they are sites of already existing wind farms, while the other 2 are near crucial hubs for marine traffic in order to facilitate the transport of hydrogen from the platform to the mainland. And after deciding the locations, we also defined the size of the different components inside the plant. And so clearly, we have to size the components depending on how much we are able to produce, or how much energy we are able to produce. So to have a complete overview of the potentiality, we decided to investigate different sizes of the farm. So starting from a nominal production of 2.2 megawatt to 33 megawatt with a step size of 2.2 megawatt, which corresponds to a situation from 2 to 30 airborne wind energy system with a step size of 2 airborne wind energy systems. And for the electrolyzer, we took 3 possible choices, which are 35, 74, and 90% of airborne wind energy system nominal power. Then we estimated the water and hydrogen maximum flow in order to identify the size of the compressor, of the water treatment system, and of the storage. And finally, we employed a different rule for the battery energy storage system, just because we were not so expert in this field. And we took like these 3 sizes, so 1 megawatt from 1 to 10 airborne in the farm, 2 megawatt from 11 to 20, and 3 megawatt from 21 to 30. So we then took data sets from ERA5 with hourly wind speed data at 300 meter height from 2050 to 2020 to estimate the performances of the farm. And we estimated the probability density functions of the wind speed. Thanks to that, we were able to also highlight the productivity time, and for the results, we can see that in the whole C1 farm, we have the best productivity, so 84% of time of productivity, and half of this time is at maximum productivity, so in this wind speed range, which is the one who allows the maximum productivity. While the other farms are less productive, and in particular, I just want to point out that the oceanic ones are better than the Marsala and Olbia, which are the Mediterranean one. And finally, the costs, just because we know that it's important to evaluate also the economical aspect in the development of the hydrogen market. So for the airborne wind energy systems, we took the levelized cost of the energy, which is 20 euros per megawatt hour. And this is a projection for 2040. It's a projection for 2040 also the cost of the electrolyzer, which is a range from 550 to 700 euros per kilowatt. And then we have water treatment system, battery energy storage system, compressor and storage, which are actual costs taken from literature or from data from suppliers. And so these are the costs that we get. And yeah, then thanks to these costs and to the productivity of the farm, we were able to estimate the cost per kilogram. We obtained this range, so with a minimum of 1.90 euros per kilogram and a maximum of 3.5 euros per kilogram. It is a quite a large range, but we also investigated why it was like this. And we saw that increasing the number of the airborne wind energy system, the cost per unit increases. But the biggest part of this range was like occupied from sizes of the farm, which are quite small. So when we reach number of airborne wind energy systems in the farm, which is equal to 10, 12 airborne, we like stabilize around 2 euros per kilogram. So the other sizes are also maybe in this part of the range. Then for the electrolyzer size, that can change. There is not the same trend, so we can have an increment or a decrease in the cost per unit. But this is probably due to the fact that the increment in the production not compensate the increment in the cost of the electrolyzer. And we also studied like the influence of every component in the cost per unit. We saw that the airborne wind energy systems and the electrolyzer are the most relevant elements in the cost per unit, while the other are much less relevant. I just want only to say that the battery energy storage system has an influence which is greater when we have like a farm with a less number of airborne wind energy systems. This is only the case of 30 airborne wind energy systems with the 3 possible sizing of the electrolyzers. So, conclusions, we can say that the electrolysis process is quite expensive, both in terms of energy and cost. we can say that 97% of energy required for the production of 1 kilo of hydrogen is required by the electrolysis process. So I think that this is quite important to know in this case. The unitary price that we obtain is near to some projection for future from other studies, but we have to say that we have here some costs that are actual, other are projection for 2040, and this was just because it was so difficult to find costs which were projection, but also costs that were actual. Not many suppliers were agreed to give me some data. And yeah, I can expect that some results can be better, but at the same time there are some factors that here were not considered, so that can increment the cost. So it is only like a starting point. And then we have to say that the Mediterranean Sea are less productive, even if they have some good results, and it is due to the fact that the wind speed was better in the oceanic ones. Some possible future developments of this type of work is for sure the introduction of the electrical connection between the airborne and the central platform, and also from the central platform to the ground. And this is important just because I know that they can increment a lot the costs, and it is a necessary part for the functioning of the facility. Then we can also evaluate the possibility to introduce pipelines for direct transport of hydrogen from a platform to mainland, which can facilitate the distribution of hydrogen. We need a further research on battery energy storage system, both for the employment and for the dimensioning. And finally, another possible development is the use of liquid hydrogen instead of gaseous one. So that's it for my presentation. So thank you for your attention.
Thank you, Sophia, for this interesting presentation. I have one quick question myself. How do you define productivity of the system? It's not the capacity factor, right?
No, we took like the wind speed, the probability density function of the wind speed, and we took also a power curve for which has a nominal power of 1.1 megawatts. So it was like our reference, and we transposed like this probability density function that was for the wind speed into the one for the productivity. Yeah, and then we evaluated the time, how much time we have like a sort of productivity. Yeah, and so we split into these 4 parts and evaluated the percentages.
Thank you.
Thank you. You mentioned, I think on slide 10 or 11, that you have 20 euros per megawatt hour as a projection for 2040.
Yeah.
But in the BBG analysis, it's the current.
No, I took I just took the curve of from the BBG analysis.
Okay, yeah. But if you took the curve in 2040, we are low, very low at 5 or 6 euros per megawatt hour.
Yeah.
So if you took the curve, it's okay, but in this
I don't know if like there are from the report that I have, it was like this. I don't know if like it's my error, or I have to check this. It's important.
I show you the,
yeah, I think it's quite important just because the Airborne Wind Energy system have a huge impact on the cost. Yeah. So yeah, it's crucial. Yeah.
Yeah, definitely. Yeah. So let's talk
yeah, really interesting. I was wondering, so my understanding is you basically use like a desalination process before converting to the hydrogen. Obviously, then you can get all that brine, which has a huge environmental impact in the surrounding areas, especially if you've got sort of a fixed installation. Have you also looked at using seawater without going through that desalination process first? So using a sort of a catalyst that can operate straight with seawater?
Oh no. Just because like I decided at first which type of electrolyzer to use, which is a polymer electrolyte membrane electrolyzer, and it requires high purity level of water. And I took that just because it's one of the most developed technology till now. So I choose to select the electrolyzer before, which is quite important. And just because like we have also the possibility to transport, it's much more difficult, but we have also the possibility to transport directly tap water to the platform. There are some other studies for wind turbines which do this. And so I just have the preference to work on the electrolyzer just before the fact of the desalinated water.
Yeah, that makes sense. My fear is just that when it comes to the company side of things doing it, then they're not going to take care of that, and then we're going to have a huge problem in 20, 30 years' time with all that brine. But yeah, thank you.
Thanks. Yeah, there's one more. I just recall I would also recommend that you link up with Voss, who will also present later, because these power curves for these megawatt sizes, we should, as a community, see that they are consistent with each other, because there are a lot of assumptions going in, especially on the large scale. Just as a reminder for everyone.
Thank you. Interesting presentation. Regarding the electrolyzer costs, so the pumping costs are also within the electrolyzer cost. The pumping of seawater.
Oh, yeah.
Because I guess the differentiating point between wind energy systems and airborne wind energy systems could be that you could get rid of the ground station generator part, maybe couple the drum as a pump to the pump directly, and then maybe you have a synergy of using the drum directly as a pump instead of spending energy.
Okay, so no, I mean
So if you go to the this one, so feed water supply and then the feed pump,
yeah.
maybe there is a possibility to explore synergy that the winch, the drum can be used in couple with the pump, and then you have differentiation with the wind turbines, because for wind turbines it's not possible.
So to produce shaft power.
Yeah.
That is in use.
Mechanical power directly to power the pump.
The power required by this process will like include. I just took
Yeah, exactly. But
some
I think for airborne wind
not-
systems it could be a differentiator. So maybe good to explore.
Okay, I will not work on that
Okay.
anymore. So,
Ah.
yeah, but it's great for maybe I don't know. Maybe in future I will.
Maybe a master's student.
Oh yeah, but yeah, thank you so much.
Thank you. Again, so, you still have a question?
Just want to correct myself, I was wrong, you're right.
Oh, okay, thank you.